this talk is about real stable polynomials and preservers. So basically, we're going to see generalizations of what Jan talked about in his talk to multivariate polynomials. So let me get started. So we say a polynomial P with n variables, z1 up to zn, is real stable if P of z1 up to zn is not equal to 0 whenever z1 up to zn is in h of n. So what is in h to the n? So what is h? I'm going to use h to denote the set of complex numbers with positive imaginary value. So these are set of complex numbers c such that the imaginary value of c is positive. Okay, so this definition means that P has no roots in the upper half complex plane, no roots where all of z1 up to zn have positive imaginary value. Okay? So I agree the first time I saw this definition, it didn't make any sense to me. It seems a bizarre definition, but hopefully, like one goal of this talk is to make this more familiar to you. So let me, before talking about examples, I want to say an equivalent definition. Hopefully this one makes more sense to some people. So it says that P is real stable if and only if for all vectors A in Rn which are positive. So every vector where all coordinates are positive, and B in R to the n, so B does not have to be positive. The univariate polynomial P of AT plus B is real rooted. Okay. So it says that in order to test a polynomial to be real stable, all you need to do is to basically look at it along this line, AT plus B, where A has all positive coordinates, and see if the corresponding polynomial is real rooted. So I want to prove this, and then I'll talk about examples. So let me prove this very quickly. So there are two directions. Let's prove the forward direction. So suppose P is real stable. I want to prove that this polynomial is real rooted. I do it by contradiction. So for the sake of contradiction, suppose P is not real rooted. Then, by definition, there exists, say, z1 up to zn with positive imaginary value. Okay? There exists z1 up to zn with positive imaginary value. Now I want to construct A and B. So I define Aj to be the imaginary value of zj, and Bj to be the real value of zj. Then, because the i's have positive imaginary value, Aj is positive. So this vector satisfies this property, and B is a real vector. Now you can easily see that P of z1 up to zn is equal to P of AT plus B. So this is a root. Sorry, there exists z1 up to zn such that P of z1 up to zn is 0. So z1 up to zn is the root of P. So this is 0, and this is 0.
Should say,
and I said
stable. You start by assuming it's not stable.
Oh yeah, you're right. Start by assuming P is not stable. So if I put T equals I, the number with imaginary value of 1, these two are exactly equal, so I get a root with, which is a complex root for this polynomial. So P of AT plus B is not real rooted, and that's a contradiction. So the original P, so this assumption is violent. Okay, so now let's prove the opposite direction. So now I want to go from here to there. So I want to assume that this polynomial is real rooted. I want to prove that the original polynomial P is real stable. Now, again, let's prove by contradiction. So suppose P of AT plus B is not real rooted. for some a which is positive and b is real. Okay. Now what I want to do is that I want to prove that I want to prove that the polynomial p is not stable. Sorry, wait a second. Yes. So so first of all, this is not real rooted. So there exists a complex root. There exists t which is complex, which such that the imaginary value of t is not equal to 0. Now, because this polynomial has real coefficients, the roots come in conjugate pairs. We already saw that in the previous talk. So there exists a root not only with non-zero imaginary value, there exists a root with imaginary value positive. Now, I'm going to define z's and prove that the polynomial p is not real stable. So now define zj to be aj t plus bj. Now, because t has positive imaginary value, aj is positive, this would be a complex number with positive imaginary value. So this says that the imaginary value of z is positive. Furthermore, p of z1 up to zn is equal to p of at plus b, and that's equal to 0. So now I get a root. So this is a root with in the upper half complex plane. Okay, so p is not real stable, and that's a contradiction. Any question? Okay, so let me give another view of this proof. So let me describe an example. Consider this polynomial 1 minus xy. This is a bivariate polynomial. Let me draw its roots in R2. So let's say this is the x line, this is the y line. If you draw the roots of this, you see exactly this picture. Okay, these two would be tangent to the x and y line. Now, if I look at every line pointing to the positive worth end, it will cross the set of roots at exactly 2 points. So this says that along every line pointing to the positive worth end, if I restrict my polynomial to that line, I will have exactly 2 roots, and because the degree of my polynomial is 2, these are exactly all of the roots. So this polynomial is real rooted along every line pointing to the positive worth end. So this says that this polynomial is real stable. So for another example, consider this polynomial, 1 plus xy. Let's draw the roots of this. Again, this is x, this is y. The roots will be like this. Now you see you can draw some lines through the positive worth end that do not cross the roots at all. So even though this polynomial has degree 2, there are some lines pointing to the positive worth end, but there are no roots in the real space. So you can draw this.
Okay.
So it's not all lines, but okay. So there are some lines pointing to the positive worth end such that if you restrict your polynomial along those lines, you see no roots. So this polynomial is not real stable. Okay. So basically, you should have this picture in mind when I talk about real stable polynomials. You can basically restrict to Rn. You can draw the roots of the polynomial, and if the polynomial is real rooted, every line pointing to the positive worth end crosses the set of roots at exactly n points. Okay. Any questions? So if not, I want to say some examples. So, example. So let me say example and non-example. So we already saw 2. 1 minus xy is an example, and 1 plus xy is a non-example. So here's another one, a1 z1 plus da 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 plus an zn for ai is positive. So this is a real stable polynomial, and the easy way to see it is that suppose z1 up to zn have positive imaginary values. So you can basically think about them as vectors in the positive half of the complex plane. So these are like z1 up to zn. Now, if a1 up to an are positive, I'm basically thinking of a convex combination of these vectors pointing to the positive orthant up to some normalization, and any convex combination of them also points to the positive orthant. So this polynomial cannot be 0 if z1 up to zn have positive imaginary value. Again, a non-example is z1 minus z2. You can just assign both of them to be I, and it's 0, so this is not real stable. Here is another one, z1, z2 up to zn. So in fact, you can see the product of any two real stable polynomial is real stable because the product of the roots of the product are just union of the roots of the two polynomials. So this is a real stable polynomial. Another one is the elementary symmetric polynomial. So you take sum over all k, sum over all s in n choose k of z to the s, where I use this notation a lot. Whenever I write z to the s, I mean product of zi for I in s. So this is called the kth elementary symmetric polynomial. So for every k, it turns out that this polynomial is real stable. I'm not going to prove this now. This is one of the exercises. We'll talk about it after this lecture. But this is another example. Good. One more example. Any univariate real stable polynomial is real rooted. Okay. So this is again a fact simple to see. Again, just using the fact that the roots of a polynomial with real coefficients come in conjugate pairs, you can easily prove this. If you have a polynomial, if your univariate real stable polynomial has a root with negative imaginary value, it must also have a root with positive imaginary value. Therefore, it's not real stable. So if it is real stable, all of the roots should be on the real line. Okay, so one other non-example is this: z1, z2 plus z3, z4. So this is a non-example. It's an important one. You can actually plug in numbers to prove that this is not a real stable polynomial. But I want to, instead of that, I want to say one theorem about real stable polynomial, which actually says a limitation of this class of polynomials. So there's a theorem of Coe, called Wagner, and later on was strengthened by Peter Brandon. Which says that the support of any homogeneous multi-affine real stable polynomial correspond to basis of a matrix. Okay? So I haven't defined what these two are. I'm going to say it in a second. But okay, this particular polynomial is homogeneous and multi-affine. And if you look at the support is really 1, 2, and 3, 4. And this doesn't correspond to a matroid because, I mean, okay, I haven't defined what a matroid is. You don't need to know it for this talk. But if you know what it is, a matroid must have an exchange property, and this set doesn't have an exchange property. So this doesn't correspond to a real stable polynomial.
You mean like support? You plug in 0, 1?
Oh, by support I mean the set of vectors that you see a monomial with those indices. Okay, you just get the set of indices of your polynomial. Now there's a generalization of this, which again I don't have time to talk about it, but basically Peller proved that for a general real estate polynomial, the support is a jump system. Okay. So we actually know what are the possibilities of the coefficients of a real estate polynomial. Let me just give a definition for these two as well. So homogeneous, if you haven't seen, a polynomial P is homogeneous if every monomial of P have the same degree. So we say P is the homogeneous if P of, let's say, alpha Z1 all the way to alpha Zn is equal to alpha to the D P of Z1 up to Z. So, for example, Z1, Z2 minus Z3 squared. This is 2 homogeneous, but 1 minus Z1 is not homogeneous. Okay. Here, this has degree 0, this has degree 1. So another definition, again, if you haven't seen, multi-affine. So you say P is multi-affine. If it is square free, if all monomials are square free. So for example, again, Z1, Z2 minus Z3 cubed is a non-example, but 1 plus Z1 minus Z1, Z2 is an example. Okay, so this polynomial, for example, is a square free and is homogeneous as well. Any question? So now, okay, so you already saw that these real estate polynomials generalize the class of real-rooted polynomials. Now you can ask, and we already saw some example. Yes?
What was the condition for Better-Brandon's theorem? Was it being a jump system? So
any real estate polynomial, the support of any real estate polynomial is a jump system.
So you don't need to be homogeneous or multi-affine. Okay.
Good. So so generally, like similar to the Jan's talk, the way you work with these polynomials is that you start from some polynomial that you know is real stable. You apply some closure properties that preserve these polynomials until you get to the polynomial of your interest. Now there's always a question of where to start, and typically in many of the proofs you start from this particular determinantal polynomial. So I've heard this name from Nishit Vishnu. I think it's a good name. Let's call it mother of all real stable polynomials. So suppose B is a D by D symmetric matrix, A1 up to AN are D by D PST matrices. Then the polynomial determinant of B plus Z1 A1 plus da 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 plus Zn AN is real stable. So today we'll see a lot of examples where we start from such a polynomial and derive some other polynomials which are real stable. So let me prove this. Questions about the statement? Oh, yeah.
Is there a converse to this? If you have a method, it can assign numbers to get.
Good. No. So that's not true. So there are matroids, like the Fano matroid, where there is no real estate polynomial whose support is the correspond to basis of the Fano matroid. And this was again proved by Peder. But again, in this workshop, we'll see a generalization of real estate polynomials called completely Lie concave polynomials, where actually you can attain all matroids as their support. Okay. So let me prove this. So the proof is by this lemma I said a few minutes ago that I raised. So basically, I again look at this along the lines to the positive orthant. So let's choose an arbitrary vector A in Rn with every coordinate is positive and B in Rn. Let's look at determinant of B plus summation of AI T plus BI times AI. Okay, so this is my polynomial. I want to say this polynomial is real rooted. And all I'm going to use eventually is that the characteristic polynomial of any symmetric matrix has only real roots. Okay? Good. So let me make my life easier. Look about the S here. Suppose these matrices are positive definite. In fact, there would be a limiting argument which extends this to all PSD matrices. But let me prove the easier statement for positive definite matrices. So suppose these AIs are positive definite. So I can rewrite this as follows. This is equal to, let me factor out the coefficient of t. This coefficient of t is just summation of AI times t plus summation of BI AI. Good. So now what do I know? I know that AIs are positive definite. These little AIs are positive. So this matrix, let's call it A, is positive definite as well. It's a sum of positive definite matrices. It must be positive definite. What do I have here? B is symmetric. These AIs are symmetric. These are real numbers, so this is symmetric. Let's call this matrix C. Okay. So all I have is just, this is really determinant of A, T plus C, where A is positive definite, C is symmetric. Now because A is positive definite, it has an inverse and a square root of inverse. So I can rewrite this as follows. I can rewrite it as determinant of A to the 1/2 Ti A to the 1/2 plus A to the -1/2 C A to the -1/2. Okay, I just factor out the A to the 1/2 from both sides. Now, I just use the fact that the determinant of AB is just the determinant of A times the determinant of B. So I can take out this A to the 1/2 to the outside. This is equal to determinant of A times determinant of Ti plus A to the -1/2 C A to the -1/2. And that's all. Basically, this is just a number. This matrix is a symmetric matrix because C is symmetric, and this is just multiplying A to the -1/2 to both sides. So this is a symmetric matrix. This is the characteristic polynomial of a symmetric matrix, so it must be real rooted. Any questions? Okay. So now I get to the more interesting part of this lecture, which are called the stability preservers. So we already learned what these stable polynomials are. Now it turns out that there are a lot of operators which preserve stability. Look, if you start from a real estate polynomial, you apply the operator, you're going to get another real estate polynomial. And that's what we want to learn now. So let me start with some. So suppose you have a polynomial P, which is with real coefficients, which is real stable. So now let's see some operators. So here's the simplest one. Let's look at P of 2z1, comma z2. So I'm saying this is real stable. And there are many easy ways to see it. Basically, if z1 has positive imaginary value, so is 2z1. So this mapping x to 2x maps upper half complex plane to upper half complex plane. So this polynomial is real stable. Any question here? So you can do some other thing. You can do, for example, z1 plus z2, comma z2 to zn. This is again the same thing. If z1 and z2 have positive imaginary values, so does z1 plus z2. You can actually do something more interesting. We can do this. You can do az plus b, where A is, let's say, is an m by n matrix, where all coordinates of A are positive, and B is a real vector. And it's the same thing. When you multiply A with Z, if Z has positive imaginary value, so is AZ. Every row of every coordinate of the vector that you get will have positive imaginary value. Okay. So a special case of this is actually when A is 0. Sorry, not A is 0. The first row of A is 0. So something like this: P of C, comma Z2 up to Zn, where C is where the imaginary value of C is positive. Not negative. That's a special case. And you can see in this case, I guess it's kind of in a special case, because I'm assuming, actually I am here allowing A to be non-negative. And the way to see it is that if C has positive imaginary value, then this is of course true, because if this has a root with positive imaginary value, so does the original thing. Now you can take limits to get to the real line, and still the corresponding polynomial will be real stable. Okay. So this particular operation is very useful for us. It's called specialization. So you can specialize not only to numbers to positive imaginary value, but also to the real line, and this will remain real stable. Okay. So in particular, yeah, you can plug in C to be 1 or 0 and still have a real stable polynomial. We'll see a lot of applications. Okay.
Well, do you consider 0 as stable?
Yeah, if you plug in 0, you also get real stable.
No, 0 polynomial equals 0.
Oh, yeah. Okay, good. So there is always a question of how you should treat the 0 polynomial, but let's treat that also as a real stable polynomial.
Okay, that's fine.
Yeah. Yeah. Good. Now, okay, so these are some operations. There are some more interesting ones. So differentiation. So if you look at partial z1 of p, and this is a stability preserver. I differentiate with respect to z1. This needs a little bit more work to prove. Basically, you need to use the Gauss-Lucas theorem. So remember, Gauss-Lucas theorem says that if you have a univariate polynomial, the roots of a derivative are in the convex hull of the roots of the original polynomial. Basically, you just need to use that to prove that this polynomial is real stable. Here is another one. If you look at p of -1 over z1, times z1 to the degree of z1, z2 all the way to zn. So this is again another stability preserver operator. And again, this, the proof is to see that if you map x to minus 1 over x, this maps upper half complex plane to upper half complex plane. So if z1 has positive imaginary value, so does minus 1 over z1, and that's all it is. Okay. Now I can keep going on writing more and more operators, but you can ask, okay, is there a general picture? Like, where is this going? And this has been studied quite extensively. So there is this very nice work of Porcia and Brandon, who actually characterized all linear operators that preserve real stability. Now, I'm not planning to say their theorem in the most general way. I want to say sort of a special case of it, which is most useful. So let me say that. So let T be an operator which maps polynomials from z1 up to zn to polynomials from z1 up to zn. Okay. And suppose it's defined as follows. So T is equal to summation of, I sum over all vectors alpha and beta. These are integer vectors, like non-negative integer vectors. So let's suppose they are in n to the n. C of alpha comma beta times z to the alpha partial to the beta. So let me say what I mean by this. So this, again, this z to the alpha is the same notation I kind of use. So this is just product of zi to the alpha I. And this thing is product of partial zi to the beta I. Okay. So let me, before continuing this, let me say some examples. So for example, T could be 1 minus z1 partial z2 plus partial z3 squared, minus 3 z4, and so on. Okay, so this is such an operator. Okay, so suppose you have such an operator T, and the question is, does this if I apply this operator to a polynomial P, which is really stable, will the new polynomial be real stable as well? Now, in order to answer that, I need to define a new thing. So now let's see. Let T be this. Now define f of T. You can think of it as a symbol of T, but this is not really a symbol. Symbol is defined differently, but let's call it symbol of T. So let's define it as follows: summation over, again, all alpha and beta, which are integer vectors. C of alpha comma beta. So again, I'm thinking of C as a real number. Z to the alpha minus W to the beta. So this f of T is a new polynomial in Z1 up to Zn and W1 up to Wn. So I'm going to have n new variables, W1 up to Wn, and I define the rest of the symbol this way. Wherever I have a partial, I substitute it with minus W of the same index. If it's partial of I, it's going to be minus Wi. Okay. So for example, if you have this f of this polynomial, let's call this Q. F of Q is let's do the exercise. It's 1 minus Z1 times minus W2 plus minus W3 squared minus 3 Z4. Okay, so it's a very simple mechanical thing you can do to construct this symbol. Okay, so now T is a stability preserver. If and only if f of T is real stable. So that's the theorem. So for example, let me state some example. Let's see 1 minus partial z1, partial z2. That's like one operator. So if I apply, if I do the f thing, this is really 1 minus w1 minus w2, which is equal to 1 minus w1 w2. And we already saw at the beginning that this is a real stable polynomial, so this is a stability preserver. Okay. Another example, 1 plus partial z1, partial z2. So you do the f thing again. In this case, you get actually 1 plus w1, w2. And we saw this one is not a stability preserver. Sorry, this one is not a real stable polynomial, so this is not a stability preserver operator. Okay. And you can ask, why is this not a stability preserver operator? So in this case, it's easy to prove. So if you apply this, if you apply this to z1, z2, you actually get 1 plus z1, z2. So even though this polynomial is real stable, when I apply it, I get a non-stable polynomial. So this is not a stability preserver operator. Any question? So okay, so first of all, you can ask how general is this theorem? What kind of operators can I express this way? It turns out that it's fairly general. So basically any linear operator acting on polynomials of bounded degree can be expressed this way. As this summation of C alpha. So it's a fairly general theorem. Good. Yes?
Is there any intuition behind construction of a Q polynomial? I mean, why that partial del is replaced by minus W?
Yes, one reason is that you want to be able to apply it to Z1 up to Zn and get the you want that to remain real stable when you apply it to Z1 up to Zn. Is that better? Good. So let me. Let me say a particular operator called map. So this is called multi-affine part. So what this operator does is that it basically kills all monomials which are not multi-affine and only retains those which are multi-affine. So when you apply map, for example, to say 1 plus z1 z2 minus 3 z3 squared plus 2 z1 z2 squared, basically I'm going to kill the last two, and this is equal to 1 plus z1 z2. Okay, so that's what map does. And so there's a simple lemma, which again is an exercise, that map is a stability preserver. So we're going to use this theorem of Porsche-Brandon to prove that map is a stability preserver operator. Okay. Any questions? So now that we have the machinery, I can tell you applications. So I want to say two applications. The first one is to prove that the matching polynomial is real rooted. And the second one is to design an approximation algorithm for the permanent of matrices with non-negative entries. So let me go to them. So application 1, the matching polynomial. Remember, it's mg of x is equal to summation of k minus 1 to the k, x to the k, mk. And mk, this is the number of matchings g of size k. So the claim is that this is real rooted. Okay, so I want to prove this using real stable polynomials and stability preserver operators. Let's prove it. So basically the proof is just 2 steps. So first, let's start from this polynomial. Let's look at the product over all edges, all I neighbor of j in the graph of 1 minus zi zj. So this is again the familiar polynomial we saw many times. It's real stable. I have product of real stable polynomials, so the product is also real stable. So this is a real stable polynomial. Now I apply map. So map of this product. This is real stable as well, because map is a stability preserver operator. Now let's think about what is the map of this polynomial. So here, basically, think of zi zj as a generating polynomial of the edge connecting I to j. Okay? When you open this up, from every term in the product, you either choose the 1 or you choose the edge. You choose the generating polynomial of the edge. Now, if I choose 2 edges which are neighbor of the same vertex I, if I choose zi zj and maybe zi zk, I'm going to have a zi squared, or maybe a higher degree of I, depending on the rest of the edges. And map will map that monomial to 0. So a monomial will survive only if all the edges that I choose don't share any endpoints. Okay? In other words, a monomial will survive if the edges that I choose form a matching. Okay? So I can say this is exactly equal to the summation over all matchings in my graph minus 1 to the size of the matching, the number of edges in the matching, times the product of zi for all vertices I which are saturated in the matching, for all vertices I which have an edge in the matching. So this is exactly this is exactly what map does. Now all you need to do is to just sort of symmetrize this polynomial, replace all zi's with the same variable x. This remains real stable. And this polynomial is exactly equal to summation over k minus 1 to the k, x to the k. This becomes x to the k, and then I have mk. Because every matching of size k will contribute 1 to the coefficient of x to the k. So I get that this polynomial is real stable. I already said that any univariate real stable polynomial must be real rooted, so I get a real rooted polynomial.
X to the 2k.
X to the 2k, yes. Oh yeah, there is a 2k here. Okay, good. Solve this. I missed that. So yeah, so this is exactly equal to mg of x. And I get that mg of x is real root. Any question?
So I think Jan's polynomial had an x to the n minus 2k, but it doesn't make a difference.
Oh, was it x to the n minus 2k?
That's also real rooted.
Yeah, then you can, you can also look at x to the n minus 2k, but you can flip the order of the coefficients, and remember that real rooted polynomials will remain real rooted when you reverse the coefficients.
But if you had x to the k, it would actually not.
No.
No, I think x to the k is okay, because if this is real rooted, it's positive rooted.
Yeah, but I think there's going to be. No, this has negative roots. This has negative roots because the coefficients are positive.
No, they're not. They're alternating.
So
this has positive roots.
Something is fishy here, because I think if you
If you raise -1 to the k and replace 2k by k, it's still real rooted, right?
Yeah.
Yes.
No, it is because the roots are positive, and this is a polynomial in x squared.
Ah,
So you can
okay.
take this
Right.
It's all.
But if you have all positive coefficients, it doesn't work.
Yeah, but you don't. You have alternate.
I know, yeah. Okay.
Yeah, it works. If you go to the simpler version with x to the k and no signs.
Yeah.
And no signs. Yes. Okay. Okay, good. So let me say the second application. So this is to approximate permanent of matrices. Let's say I have a matrix M, n by n matrix with non-negative entries. I want to approximate the permanent. So first let me remind you what the permanent is. The permanent of M is just the sum over all permutation sigma, the product of M of I comma sigma I, or I. So that's the permanent. It's a quantity which is sharply hard to compute. The best approximation algorithm that we know is due to Jerome Sinclair and Vigoda. Which is polynomial time, which is randomized polynomial time. And it gives 1 plus or minus epsilon approximation to this quantity. Now there is a big open problem of if you can get a good deterministic approximation algorithm for this. There are a lot of works in this. So let me briefly mention. So there's this work of Lineal, Samordonitsky, and Wittgerson from '98, and then Gurwitz from '04, and then there's Gurwitz, Samordonitsky from '14, and then the newer work of Anari and Rezai from 18. So basically all these give some constant to the n approximation. The best that we know at the moment is root 2 to the n approximation. And it's open to get better approximation algorithm deterministically. So this is again deterministic. It's open to get better approximation deterministically. I want to talk about this result because it's quite short and it actually has a lot of other applications besides the permanent. So here is a theorem of Gurwitz. So let P be real stable with non-negative coefficients. We proved that if I take partial z1 up to partial zn of p at z equal to 0, so you differentiate p with respect to z1 up to zn, then you evaluate it at 0. What this means is that this is really the coefficient of the monomial z1 up to zn in p. Okay? So look at the coefficient of this particular monomial. It is, you can approximate it this way by looking at infimum of p over z1 up to zn for z positive, and e to the minus n times the infimum of the same thing. Okay? So it's sandwiched between this quantity and e to the minus n of the same quantity. Okay? So if I can compute this quantity, I can approximate the coefficient of z1 up to zn up to e to the n error multiplicatively. Okay, so that's the theorem. So why is it useful? So application to permanent. So here's the application. Let P be, so again, fix this matrix M that we have. We want to compute the permanent. Let P be the be the product over I, sum over j of mij zj. So the coordinates of the entries of M are non-negative, so this is a real estate polynomial. I have a product of real estate polynomials, so P is real stable. So, and it also has non-negative coefficients, again, because its M's are non-negative. So I have a polynomial P, and the claim is that basically coefficient of z1 up to zn at P is equal to permanent of n. So all I need to do is to just compute this number, and that's the permanent of n. Okay. The way to see this, okay, there are many ways to see this. You can basically see that P is this product of these sums. So if I want to get z1 up to zn, I have to choose one zj, like exactly one zj from each sum, and that corresponds to a particular permutation, which gives me the to give me a z1 up to zn monomial. We can also do some examples, but let me not talk about the proof of this. This is a simple thing to check. It's identity. So in order to approximate permanent, all you need to do is to approximate this quantity. And it turns out that you can approximate this quantity just by convex programming. So okay, so this function is not convex on its own, but you can do a change of variable and make it a convex function. So in particular, if you look at log of this function, meaning log of P over z1 up to zn, where you do a change of variable, so you substitute zj with e to the yj. So yj is really log of zj. So I look at P of e to the y1 all the way to e to the yn over e to the y1 e to the yn. So log of this is really log of P of e to the y1 up to e to the yn minus y1 minus minus yn. So if you look at this, I claim that this is a convex function of y's. First of all, the second part is a linear term in y's. The first term is a convex function of y's because this is really a log sum x expression. It's a log of summation of exponentials. Again, I'm using that P has non-negative coefficients. So you can really think of this as log of summation of some exponentials. And so this is a convex function. This is a convex function. The sum of two convex functions is convex. So this is convex. So you can minimize this. So again, you can optimize this quantity, and that would give an e to the n approximation to the permanent. Okay, so good. So running out of time. Let me so here let me try to prove half of this. I'll leave parts of the proof for the exercise. So I want to prove this identity, but prove half of it. Any question so far? So okay. So there are two sides to this inequality. This side is the easy side, and this side is the hard side. So let's see. The easy side, actually, you don't need the polynomial to be real stable. You just need the polynomial to have non-negative coefficients. And the reason is that, okay, I can basically think of P of z1 up to zn over z1 up to zn as follows. I can basically pull off the term which is the coefficient of z1 up to zn plus some extra. This is really the C I'm interested in the middle side. This is the coefficient of z1 up to zn. And then, okay, so the division is really C plus this extra stuff over z1 up to zn. And the thing is, this is non-negative because all coefficients of P are non-negative, and I'm evaluating this quantity on non-negative reals. So this is non-negative, so this is at least C. Okay, so for the right-hand side, you don't really need P to be real stable. It's only that you need P to be real stable for the left-hand side. So let me prove the left-hand side. The proof is the proof of the left-hand side. The proof is a simple sort of, it's a tricky but short inductive argument. So let's induct on n the number of variables. Okay. So let's prove the base case. Let's talk about the base case first. The base case is when n equals 1. Okay. So what? Let me write it. This is exactly the homework problem, the sort of in-class exercise problem. So suppose you have a polynomial f of a single variable t, and f is real rooted or real stable. And remember, for univariate, real rooted and real stable are the same. So it's real rooted, non-negative coefficients. Then f prime at 0 is at least 1 over e times the infimum of f at t over t. Okay. So this is really the same thing, except when n is equal to 1. Okay, and this e to the minus n becomes e to the minus 1. Okay, so I'm not going to prove this. I will prove it in the exercise section. But let's take this for granted, and now let's do induction. Okay, so I want to induct an n, so this is the base case. Now define Q to be partial Zn of P at Zn equals 0. Okay, so I just killed off one variable. Now I have Q. Q has n minus 1 variable. So Q is only on Z1 up to Zn minus 1. We have only n minus 1 variables. Therefore, I can use induction hypothesis applied on Q. Remember that. So remember that Q is real stable, right? Because all I did is that I differentiate and specialized. And both of these operations preserve real stability. So yeah. So this and this are a stability preserver. So Q is real stable. And it has non-negative coefficients. This again you can see because, you can just easily see differentiation and plugging in non-negative values will preserve non-negative coefficients. So I can apply induction hypothesis to Q. So by induction hypothesis, partial Z1 up to partial Zn minus 1 of Q at 0 is at least 1 over e to the n minus 1 of infimum of Q over Z1 up to Zn minus 1. Okay, that's the induction hypothesis. Now, so first I claim that this thing is exactly equal to the left-hand side. This is really partial Z1 up to partial Zn of P at 0. Because Q, remember Q was just differentiating P at Zn and then evaluating at 0. And I'm just changing the order of differentiation and substitution, but these operators are commutable, so you can change the order. So this is really equal to the left-hand side. Now I want to relate this to the right-hand side. Okay, so here's what I do. Let's say I assume that this infimum is attained at some point. I'm cheating a little bit, but let's do that. You really need to do epsilon delta argument, but let's make the argument simpler. So suppose this is equal to 1 over e to the n minus 1 of Q of Z1 star, Zn minus 1 star, over Z1 star, Zn minus 1 star. So I'm assuming that this infimum is attained at Z1 star up to Zn minus 1 star. Okay, good. Now, one more step. So now define f to be p of Z1 star. So it's a univariate polynomial. F of Zn to be p of Z1 star up to Zn minus 1 star, comma Zn. Okay. So I specialize to Z1 star up to Zn minus 1 star. Again, f is real rooted and non-negative coefficients because I just specialized to non-negative numbers, and this Z1 star up to Zn minus 1 star are non-negative. So f is real rooted and non-negative coefficients. So I can apply this base case again to f. So I get that basically f prime at 0 is at least 1 over e times the infimum of f of Zn over Zn. Okay, that's just by the base case. Now, f prime at 0 is equal to exactly this quantity, to q of z1 star up to zn minus 1 star. Because remember, f is just differentiating this with respect to zn. F prime of 0 is just differentiating this with respect to zn at 0, and that's exactly q of z1 star up to zn minus 1 star. So this is equal to that. Now we're almost done. Now divide both sides by z1 star up to zn minus 1 star. z1 star, zn minus 1 star. Let's see that here. Then, then this is equal to 1 over e times infimum of. Now I replace f with p, right? This is really p of z1 star up to zn minus 1 star, comma zn, over z1 star, zn minus 1 star, comma zn. And the infimum is only over zn. But now I can take the infimum to be over all z's, and that can only make it smaller. So this is bigger than or equal to 1 over e times the infimum over all z1 up to zn to be non-negative of p of z1 up to zn over z1 up to zn. That's it. So I get 1 over e from here, 1 over e to the n minus 1 from there. That's all I get. Over time, but let's stop here. If there are no questions, then we can continue with the break.
Is this bound of e to the n type this level of generality?
Yes. Yeah. Yes. So you can. So there is this class of polynomials. So you can work with e to the n itself. That's not really a polynomial, but of bounded degree, but if you plug that in, that would actually give, like you work with e to the z1 plus z2 up to zn. That would preserve all properties of real estate polynomials, and it would be tight for that.
I guess you could truncate the sequence of polynomials.
Truncate?
Truncate like the Taylor expansion.
Yes, you can truncate. Yeah. But yeah, you can get truncated, but yeah, if you want to be very careful. But usually that would give you a tight example for many of these things. Yeah, that would make it a little bit more messy. Yes. Right. Any other questions? Okay.